Hello everyone. Welcome to the fifth section of my tutorial on data pricing from economics to data science. This section is about pricing data products. In this section, we will discuss pricing in marketplaces of data. We will first obtain an overall understanding about data markets and the major players in such markets. Then, we will look into several most studied technical problems in data product pricing, including arbitrage-free pricing, fair and truthful pricing, privacy preservation in data marketplaces, and pricing dynamic data and online pricing. First, let's look at data markets and pricing. What are they? Marketplaces for data have been actively being developed for over a decade. An early survey identifies different categories and dimensions of data marketplaces and data vendors in 2012. There are many studies on various issues about data markets and pricing strategies. Before we discuss any specifics in detail, it is important to obtain an overall understanding about data markets, such as what are sold and for what purposes, who are the sellers, who are the buyers, and what are the basic pricing models. Pantelis and Aja present a brief economic analysis of data taxonomy as a market mechanism. Data and databases are legally protected by either copyright or database rights. Copyright protects expressions and significant creative effort that creates and organizes data. Database right protects a whole database. One challenge here is that both copyright and database right are hard to enforce due to the non-rivalrous nature of data. In general, data may be owned by governments, private parties, or individuals. Consequently, data can be categorized into three types: open data, public data, and private data. Open data are common pool resources such as the data made available by the Open Data Initiative. Public data, such as the data collected by the government in the United States, are valuable resources subject to the tragedy of the commons. Public data are often produced by individuals or organizations for research and used by governments and local authorities, but may also be employed by commercial parties to enhance their proprietary resources or services. Private data are generated by private applications or services. To understand what are sold in data markets and for what purposes, Musgrave et al. Consider the common queries and demands on data markets, as well as the pricing strategies. They observed two major types of queries. The first type of queries are to estimate the value of a thing or compare the values of things, where examples of the things include web pages for advertisements, starlets, predictions, and products. The second type is to show all about a thing. Those queries are raised by 7 categories of beneficiaries, namely analysts, application vendors, data processing algorithms developers, data providers, consultants, licensing, and certification entities, and data market owners. They also identify three types of market structures. First, in a monopoly, a supplier is powerful enough to set prices to maximize profits. Second, an oligopoly is dominated by a small number of strong competitors. Last, in strong competition markets, prices may align with marginal costs. A series of pricing strategies and models may be considered in data markets. First, free data may be obtained from public authorities and may help to attract customers and suppliers of commercial data and be integrated into private, not free data products. Second, prices can be based on usage, such as charging customers per hour of data usage. Third, package pricing allows a customer to obtain a certain amount of data or API calls for fixed fee. A few studies try to optimize package pricing models. Fourth, in the flat fee tariff model, the data product or service is offered at a flat rate, regardless of usage. It is simple, easy to use. The drawback is the lack of flexibility, particularly for buyers. Fifth, combining package pricing and flat fee tariff results in two-party tariff, that is, a fixed basic fee plus additional fee per unit consumed. This model is popular in data services. Specifically, Wu and Banker show that under zero marginal costs and monitoring costs, flat fee and two-part tariff pricing are on par, and two-part tariff is the most profitable strategy. Last, in the freemium model, users can use basic products or services for free and pay for premium functions or services. Recently, machine learning, particularly deep learning, becomes disruptive in many applications, such as computer vision and natural language processing. In most situations, powerful deep models heavily rely on large amounts of training data. Monetization of data and machine learning models built on data through markets gains stronger and stronger interest from industry. Specific to data as an economic good and data pricing as a monetization mechanism in this context, a series of studies focus on data utility for model building and the associated pricing, particularly considering privacy. Some data owners may have detailed knowledge of specific machine learning tasks and thus dedicate corresponding effort to collect high-quality data for building better models. Babiarov et al. Study the design of optimal mechanisms for a monopoly data provider to sell her or his data. Specifically, they show that it is feasible to achieve optimal revenue by a simple one-round protocol. That is, a protocol where the buyer and seller each sends a single message, and there is a single money transfer. The optimal mechanism can be computed in polynomial time. For a buyer who may abort the interaction with a seller prematurely, multiple rounds of partial information disclosure interleaved by payments may be needed to ensure optimal revenue. Cummings et al. Study the optimal design for data buyers to purchase data estimators with different variants and combine the estimators to meet a required quality guarantee on variants with the lowest total cost. The role of privacy in data collection and machine learning model building is investigated. For example, Ghosh and Roth develop auctions that are truthful and approximately optimal for data buyers to obtain accurate estimates on data from vendors who are compensated for privacy loss. They show that the classic Vickery auction can minimize the buyer's total payment and meets the accuracy requirement. In general, modeling data owners' cost of privacy loss is very difficult since the cost may be correlated with private data arbitrary. It is impossible to design a direct revelation mechanism that can provide a non-trivial guarantee on accuracy. And at the same time, it is rational for individual data owners. To tackle the issue, Liggett and Ruth designed a take it or leave it mechanism by randomly approaching individuals from a population and making offers. These mechanisms can be used for some data collection scenarios such as surveys. Versioning is an important strategy in data pricing. A data seller can customize data into different versions according to buyers' needs. Buckman et al. Developed the optimal menu of information products that a monopoly data supplier can offer to a data buyer, so that one product can fit the buyer's willingness to buy the information at the offered price, and the revenue is maximized. One important finding is that information products indeed allowed large scope of price discrimination. There are at least two dimensions that can be explored by sellers to derive various subsets of a dataset, namely the data quality and data position. When data are used to build machine learning models, it is important to assess the value of each datum, that is, a data record within a dataset. Various methods exist for assessment, such as leave one out, leverage on inference score. Gopani and Zhou proposed to apply the Shapley fairness on data used to train a machine learning model, and thus define data Shapley for a record I as the formula shown here. Where one challenge is that computing the exact data Shapley value on large datasets for sophisticated models such as deep neural networks is computationally prohibitive. They also provide Monte-Carlo and gradient-based methods for estimation. Data quality is an important issue. There are many studies on assessment of data quality. Some studies specifically focus on pricing based on data quality and the impact on data markets. Heckman proposed a simple linear model such that the value of data is the sum of the fixed cost and a weighted sum of the factors, where the factors include but are not limited to age of data, periodicity of data, volume of data, and accuracy of data. And the weight Wi is the associated weight, and thus the parameters in the model are hard to estimate. One practical difficulty in using the model is that many datasets do not have public prices associated. Yu and Zhang considered pricing multiple versions formed by multiple factors of data quality. They built a two-level model. The first level is the data platform where a single owner is assumed, who assigns the number of versions. The second level is the customers who want to maximize the data utility. Each level is modeled as a maximization problem, and thus the whole model is a bi-level programming problem, which is NP-hard. Another way to form multiple versions of data products is to charge by queries. Intuitively, a data seller may treat a view of a dataset as a version. Setting the price for every possible view is not only tedious but also tricky. If prices on views are not set properly, arbitrage or less than highest prices may happen. Hodges et al. Propose a framework of query and view-based data pricing. The major idea is that the seller only needs to specify on a few views, and then the prices of other views can be decided algorithmically. They advocate two declarators, arbitrage-free and discount-free. Theoretically, they show that the existence and uniqueness of pricing functions satisfying the requirements. They also show the complexity of computing the pricing functions. Unfortunately, only selection views and conjunctive queries without self-joins are tractable. They present polynomial time algorithms for chain queries and cyclic queries. Technically, the core idea in view and query-based pricing framework is query determinacy. A query queue is said to be determined by a set of views V if the answer to Q can be derived from only the views. Query determinacy enables the feasibility of arbitrary-free detection. If V determines Q, then arbitrage happens if and only if the price of V is cheaper than that of Q. Hodges et al. Further explore the technical challenges in practical implementation of view and query-based data pricing. Specifically, they develop an integer linear programming formulation for the pricing problem with a large number of queries. Considering the scenario where a user may purchase multiple queries over time or the database is updated, such that information in multiple queries and updates may have overlaps. They also leverage query history to avoid double charging. To handle the situation where there are multiple sellers, they define the share of a seller as the maximum revenue that the seller can get among all minimum cost solutions. And accordingly, they defined a fair revenue distribution policy. They also demonstrate a prototype system. Tang et al. Follows the view and query-based pricing framework, but consider the minimum granularity of data. That is, each tuple is a view. Their model assigns to each tuple a price and prices queries based on minimum provenance. Tang et al. Extend view and query-based pricing to XML documents and consider the situation where a customer may just want to purchase a sample instead of the complete query result. Arbitrage-free pricing. Arbitrage is probably the most intensively studied issue in pricing data products. As introduced in the last section, in general, arbitrage is the activities that take advantage of price differences between two or more markets or channels. Arbitrage is undesirable in many pricing models. Unfortunately, arbitrage may slide into pricing models without rigorous design. For example, Balazinska et al. Analyzed the subscription-based pricing, possibly with a query limit allows arbitrage. Marshall et al. Point out that the pricing model of charging users a certain amount of API calls for a fixed rate may potentially allow arbitrage, depending on the package size. Being arbitrage-free is one of the fundamental properties of pricing models in query and view-based pricing. Lee and McLeod and Lee et al. Developed frameworks of pricing linear aggregate queries. Specifically, Lee et al. Consider linear queries. Given a dataset of n tuples x1, x2 to xn, a linear query Q, which is a set of Q1, Q2 to Q big N, is a real valued vector. And the answer Qx is the sum of the Qi on Xi. For a multiset of queries S, which is equals Q1 to Qk, and query Q, big Q, if the answer to Q can be linearly derived from the answers to queries in this big S, then Q is said to be determined by S. A pricing function πQ is arbitrage-free if for any multiset S and query set Q, such that this S determines Q, the price of Q should be less than the total price of this Qi. Under the general intuition of arbitrage-freeness, Lee et al. Consider a specific form of queries, linear queries with variance QV. That is, the estimation of the answer to query Q should have a variance no larger than V. Using different values of V, different versions can be formed. A pricing model not carefully designed may allow arbitrage. Lee et al. First established the observation that indeed the price of Q given V is omega 1 over V. Then they synthesized pricing function, which is arbitrary if the f is positive and semi-known. For any arbitrary pricing functions pi1 to pi k, they can apply this f to achieve an arbitrary-free pricing if this f is subadditive and non-decreasing function. As Ruth summarizes, the framework by Lee et al. Still faces three important challenges. First, arbitrage is still possible to derive answers to a bundle of queries from another bundle of queries and their answers. Second, arbitrage is still possible on biased estimators for statistical queries. Last, it is unclear whether we can obtain arbitrage-free pricing maximizing profit given the distribution of buyer demands. Later, Deep and coaches provide some interesting insights to bundle arbitrage-free pricing. Lin and Kiefer investigate arbitrage-free pricing for general data queries. They consider three types of pricing models for query bundles, where a query bundle is a set of queries posted simultaneously as a batch. First, an instance-independent pricing function depends on the query bundle but not the database instance. Second, an upfront dependent pricing function depends on both the query bundle and the database instance. A customer knows an upfront dependent pricing function and decides whether to purchase or not the query answers. Last, a delayed pricing function depends on both the query bundle and the answer computed by the query bundle on the current database instance. The customer knows the pricing function, but does not know the exact price. Once agreeing, the customer is charged with the answer that are computed. They also summarize 5 different types of arbitrage situations. First, if prices are quoted by queries, in order to avoid this price-based arbitrage, answers to queries should not be deduced from prices alone. Second, a buyer may use multiple accounts to derive answers to a query bundle. To avoid separate account arbitrage, the price of a query bundle Q1, Q2 should be at most the sum of the prices of Q1 and Q2. Third, if the answers to a query bundle QPi can always be deduced from answers to another query bundle Q, to prevent post-processing arbitrage from happening, the price of Q should be no cheaper than that of QPi. Fourth, although the answers to a query bundle Q may not be always derivable from the answers to another query bundle QPi on all database instances, still for a specific database instance I, the answers to Q may be derived from the answers to QPi. If so, a serendipitous arbitrage happens. Last, if two queries behave almost identical but their prices are dramatically different, almost certain arbitrage happens. Based on the above categorization, they discuss conditions that can prevent various types of arbitrage situations from happening. Pricing many queries in real time with formal guarantees on arbitrage-freeness is challenging. Many theoretical methods are not scalable in practice. For example, it takes query market about 1 minute to compute the price of a joint query over a relation of about 1,000 tuples. Hirana is a system for query-based pricing. The system allows data sellers to choose from a set of pricing functions that are information arbitrage-free, which covers both post-processing arbitrage-free and serendipitous arbitrage-free in Lin and Kiefer's taxonomy. Hirana also supports history-aware pricing. Hirana has been shown highly efficient and scalable on the TPCH and SSB benchmark datasets as demonstration. The key idea in Hirana is that it regards a query as an uncertainty reduction mechanism. Initially, a buyer faces a set of possible databases I defined by a database schema, primary keys, and predefined constraints. Once a buyer obtains the answer E to a query Q, all possible databases D such that the answer on these databases D are not E can be eliminated. The price assigned to Q should be a function of how much the set of possible databases shrinks. For example, if we can let S be the set of possible databases before the query Q is answered, S is called the support set. Then, the weighted coverage function assigns a weight Wi to every database Di in this S and computes the price to a query by the P QD is the sum of such Wi for all the databases whose answer is not the same as D. Alternatively, we can consider the equivalence relation in this S. We say two database instances Di and Dj are equivalent in this sense if and only if they have the same answer. Assign to each possible databases Di a weight Wi such that the sum of all the weights over all the databases in this S is 1. So let PQ be the set of equivalent classes. For each class B, denoted by this WB, which is the sum of all the members in this class, then the Shannon entropy function computes the price of query Q as the entropy of the query output. Indeed, Deep and Quatters show that the weighted coverage function, the Shannon entropy function, and the two entropy functions are all arbitrage-free. Using the complete set of possible databases as the support set leads to a Sharpie-hard problem. To make the price calculation computationally feasible, Hirana uses uniformed random sample and random neighborhoods as the support sets. In targeted advertising markets, user data such as opt-in email addresses and user impressions are sold as data products. How to price users properly to avoid arbitrage is important. Xia and Mathakrishnan consider the following problem. Denote by this QI a selection query over user attributes. By this big UI, the set of all users satisfying QI. And by PI, the price of each user in this big UI. If a user purchases n users in this big UI, he has to pay small n times PI. If prices of different queries are not well coordinated, version arbitrage may arise. If two queries Qi and Qj return similar users but Pi is dramatically more expensive than Pj, then a user who wants Qi may purchase Qj instead. Xia and Krishnan point out that uniform pricing, that is, every query has the same price, is arbitrage-free, but is a logarithmic approximation to the maximum revenue arbitrage-free pricing function. Then they present a greedy, non-uniform pricing design. The design starts with the optimal uniform pricing that is arbitrage-free, and then iteratively updates the pricing function. If the price of a query can be updated to increase the revenue, it is increased so that the arbitrage-free property is retained. This greedy algorithm is still a logarithmic approximation to the maximum revenue arbitrage-free pricing solution. Chen et al. Developed an arbitrage-free pricing design for multiple versions of machine learning models. They assume that the broker trains the optimal model on the complete raw data. Then, random Gaussian noises are added to the optimal model to produce different versions for different buyers. The rationale here is that the error of a machine learning model instance is monotonic with respect to the variance of the noise injected into the model. In this setting, a pricing function is arbitrage-free if and only if the price of a randomized model instance is monotonically increasing and subadditive with respect to the inverse of the variance. As explained in the previous section, the objective of maximization, revenue maximization, is often of specific interest in designing pricing strategies. Since for a business to be successful long-term, a more immediate and important requirement is to win over as many customers as possible. Revenue maximization pricing for data products is a relatively less explored area. As mentioned earlier, Xia and Krishnan developed logarithmic approximation pricing algorithms for revenue maximization in user-based markets. They also consider the situations where both the maximum number and the minimum number of users that a buyer purchases are specific, and provided an OD approximation algorithm to revenue maximization, where D is the largest minimum demand among all buyers. Kola consider query and view-based pricing for arbitrage-free revenue maximization under the assumption that all buyers are single-minded and the supply is unlimited. Here, a buyer is single-minded if the buyer wants to purchase the answer to a single set of queries. They consider three types of pricing functions. Uniform bundle pricing functions set the price of every bundle identically. Active or item pricing prices each item and charges a bundle the sum of prices for the items in the bundle. Fractionally subactive pricing, or XOS, sets k weights wj1 to wjk for each item j. And for a bundle E, the price is set to maximize the sum of all the wji Building on the extensive studies on revenue maximization with single-minded buyers and unlimited supply, they developed new heuristics. Specifically, it is well known that there exists uniform bundle pricing that is O log M approximation of revenue maximization, where M is the number of bundles. Swamy and Chung show that item pricing can achieve an O log B approximation of maximal revenue, where B is the maximum number of bundles an item can be involved. Chola et al. Show some new lower bounds, that is, uniform bundle pricing, item pricing, and XOS pricing combining a constant number of item pricing functions are still omega log M away from maximum revenue. They also present approximation algorithms. To maximize revenue in machine learning models, Chen et al. Show that the optimization problem is co-NP hard. Then they relax the sub-additive constraint for every xn less than y and turn to finding a pricing function QD such that Qx over x is decreasing with respect to x. They show that for every well-standing pricing function P, there exists a pricing function Qx with the relaxed sub-additive constraint such that this Px over 2 is less than Qx less than Px. And Qx can be computed using dynamic programming in O n squared time, where n is the number of interpolated price points.